We'll have two closing sessions, one now and one later. Elizabeth and Elena,
Also, also get flowers.
I'm actually recording.
Okay.
We really enjoyed it.
Wow, thank you very much.
It was a very special conference. Thank you very much. And then, like, so the, yes, there's more organizers.
So that is-
Liberato, coming. It's for you, Liberato.
So this is the first closing part. I will read it.
Thank you so much. It was so nice. Such a great conference.
So this is from all the students who participated. And
All the other organizers as well. Thank you for you.
wow,
I love
fantastic.
it.
Grazie. So I'm going to read it maybe for the organizers. Dear organizers, we would like to thank you for a lovely, insightful workshop. We very much enjoyed the talks as well as the culture program. It was a great experience for all of us. Thank you very much. Fantastic. This was unexpected. So thank you very much. Really appreciate it. And again, remember, in the afternoon we are here, and we will have the final closing part of the conference. Thank you. So now we will have the discussion session again, and the moderator is Fabio Briscese from Roma Tre University.
Okay, so let's start this session. I'd like to invite you to resume in a few minutes your talk and what's the message you want to send. Well, so maybe you can resume what's the message you want to send to the audience with your talk. And then we start the discussion. Yeah, you can use the mic.
Okay, hello. Yeah. So, yeah, my message is quite simple. Yeah, unfortunately, in the long span, at least collider on Earth is going to at least energy scale of the collider on Earth is going to saturate because of the radius of Earth is limited. So, in any way, if we are interested, of course, we don't know in which scale we have a energy scale of the beyond the standard model. Now, naturalness or hierarchy problem, we don't have a good solution. So anyway, we have to go into the higher and higher energy scale. But we don't know, at least in the long span, collider on Earth might not be so useful. So we need alternative or at least complementary one. So one promising way is going to go beyond Earth, that is just a universe. And the cosmological collider is a very suitable for to probe the peaks beyond the standard model, but at the Hubble scale during the inflation. So this is also quite nice somehow because as I told you before, apparently it requires a fine-tuning of the mass scale of the new particle, but during the inflation, somehow it's quite natural to acquire such an effective mass of the Hubble scale or scalar field or all field. So in some sense, it's natural, quite natural to observe such an effect of the heavy particle. On the other hand, effective mass over such a feature might not be what particle physics or we are really looking for. So still, if we claim that the cosmological collider can be alternative to collider on Earth, we need to invent new technique to probe the information of the new particle or DSM at current universe from the cosmological criteria. This is my message. Thank you very much.
Thank you.
Thank you. So yeah, I talked about black holes and how we have conceptual problems, and we know that this is a place where we know we need more fundamental theory. It's also a place where it's extremely difficult, if not impossible, to probe the effect of this new theory. So I think it's still very, even if it's so difficult, it's still very interesting to study what are these possibilities and to understand theoretically which of these possibilities is more likely to be. And maybe we'll find some new qualitative effect that we will never be able to find without studying the problem. For instance, I often give the example of gravitational waves. If we, of course, we introduced general relativity for other reasons. We had experimental data to explain, and we made a prediction. But without introducing general relativity, we will never be able to imagine an effect like gravitational waves. So without studying what this new object can be, maybe there will be some qualitative new effects. I'm not saying this is likely, but it's very fascinating, and I hope that we will find something. And also, we have so much data in the future, so much new experiments. So it is definitely an exciting moment, even though it's maybe unlikely. But fundamental physics is always very unlikely, and maybe something will come up to at some point. But yeah, this was my summary.
Okay. I think my message is, one of my main messages is that neutrino oscillations are very interesting because it goes beyond beyond standard model for sure, and we're seeing beyond some common beliefs, let me say. So just an anecdote. Some years ago, I was reading this book that the more mathematical of you know, the Filippo Logunov, axiomatic field theory, describing the classification made by Wigner originally of particles in terms of Casimir's of Poincaré group. And it was just footnote saying, yeah, but this does not apply for unstable particles, strictly speaking. And it impressed me. And then there were the works by Bernardini, Maiani, and Testa that I showed you, for example, where they showed that you can get some physics, quantum zero effects, going beyond this, let me say, standard asymptotic picture. And nowadays, neutrino oscillation. I'm not saying that S-matrix is not good. It works for scattering processes most of the time, but it does not work for neutrino oscillation, for example. And so, just to remind that sometimes that S-matrix was not put there by God, but was put there by physicists of the 30s, so 40s, and we can go beyond now in 2025 with new concepts, even at this level. Okay, that's what I wanted to say.
The last talk, so I'm not sure I'd like to repeat myself, but it's just one thing that we have to keep in mind, that we don't test validity of models, but we just consistency of the models, and that given that finally we have inspired model from some kind of fundamental theory, I would suggest that we should focus in qualitative and not quantitative predictions of these theories, because there are many unknown things under the carpet. We should be very careful. So, it's into one. And that, of course, with gravitational waves, we can test many of these things.
Okay, so we can start the question and answer session. So, are questions from the audience? Okay. So,
One, two, three. Just go 1, 2, 3. You need the microphone.
yeah.
There's no other microphone.
Maybe
You can use that one. Keep it in the
okay. Use this for the moment. Then. Okay.
So, my question is for Masahide, but of course it's going to extend for all the speakers, so thank you for the nice talk. The point is that we got into the saturation of the collider physics. So, we, as a theoretical physicist, we develop models that on large collider can prove or can corroborate a theory or disprove it, and then we go to the biggest one, the next big collider, and spending time in redo the theory. And this is I think that this is the same mechanism we can think about, these cosmological correlators, because a lot of people is spending time in developing the techniques for computing cosmological correlators, and then we expect that next generation of elevator will be enough sensible to prove or disprove, to corroborate or disprove our theories. So why can we expect that we are so far from the saturation point, experimentally speaking, of these detectors, and we are not, how can I say, that we are not facing a scenario that we will be in a saturation point in the next future. Thank you.
So maybe I have not yet got your point correctly, probably, but what do you mean by the saturation point? So
the point when experiment cannot be, competitive with the prediction that theoretical physicists can do.
Yeah. So this is, difficult question. But for example, in case of the collider on Earth, clear point is that the energy scale could be saturated. But in case of the cosmological collider, as long as the new physics scale is lower than the Hubble scale during inflation, in principle we can prove. So in its sense, saturation point is the Hubble scale during inflation. Yeah. But as I told you before, even in that case, we can prove only that the Hubble scale. So if the new physics scale is much lower than the Hubble scale, we cannot even identify which scale could be the new physics scale. So this is the problem point. Of course, it's fantastic to find a new particle, but if we can identify the new physics scale beyond the standard model, much better. This is the point. And, I think the saturation scale is, in case of the cosmological collider, Hubble scale during inflation.
More questions?
I have a question from Myra. You mentioned the Takuta metric in order to study
What?
the Takuta metric.
Which one?
The metric to study black holes in expanding space-time. But I think you also said it's not the full story, and actually that it changes the observational bounds in primordial black holes quite a bit. Could you maybe expand a bit on that?
I'm sorry, I didn't understand which method you do.
So the metric you said that if you want to look at primordial black holes in the universe, you have to take into account that the universe expands.
Yeah, exactly. So the question is, in which is the correct metric in order to study primordial black holes in an expanded universe? And it's not the Schwarzschild one. And that's something that we know from the past. I mean, it's something that has been pointed out by Hawking, then by Bernard Carr, but it was never worked out. So there are different proposals, and we took this Takor metric just because asymptotically it goes to a FLRW metric, and it doesn't have pathologies, but I'm not saying that this is the metric. I have discussed with a couple of relativists, they didn't know how to deal with that. It's a question which is open. If I use this Takura metric, I cannot define the ADN mass as it is for standard, So then the whole approach of how you can form binaries, the constraints are different. And that is why you can evade the LDK constraints on the major rate of primordial black holes, follow that metric, which I'm not claiming that is the metric. This is an example though, and it would be very interesting to find out which is the correct way to do that. Certainly is not what exists in the literature, what people use in order to debate whether early or late BPH formation of primordial black holes could be in agreement with LDK rate.
So, what is the problem with the metric at the moment?
I'm telling you, it is in an expanding background, so it's not a Schwarzschild metric. So it's not.
Yes, no, I mean, so you said that.
I don't know which is the metric that one has to use. I took an example of a metric that does it. So the constraints that you have to find in order for the thing to decouple from the background and form a binary are different. I can show you the questions, I didn't put them there. And if you study them, these constraints, you will realize that these primordial black holes, they had emerged much before the discovery of the LBK. So they cannot be constrained by this data.
Okay,
That's all.
But this correction to the metric that you mentioned, it should be important only if the black holes are comparable to the Hubble.
Yes.
Once they are smaller than the Hubble, then
Yes,
sorry.
yes, exactly.
So, and you are saying at that time formation of the binaries, of course, yeah. That in that case, it's important.
That's what, yeah, exactly.
Yeah.
That's what I'm saying.
Right.
That's all I'm saying.
Yeah, thanks.
Well, I really don't understand this in the sense that simulation of primordial black hole shows very clearly that when you form the black hole, they detach completely from the expanding universe. So that's what I do, I can show you. For a primordial black hole, during the collapse, the solution, the set similar solution, completely ignoring what happened inside, working. So this is something that I really don't understand.
Well, I don't understand this what you say there because
No, I mean, this is a solution. This is what the primordial black hole are characterized by self-similar solutions. That works exactly as, I mean, there is a transition from the
So my question is, so the question that I pose there is, what is the effect of these primordial black holes on surrounding material? Because is that the constraint that I want in order for a binary to be formed?
I can tell you. For LBK black holes, totally negligible. The accretion is important for primordial black holes above 10 to the 3, 10 to the 4 solar masses. For LBK, this is totally negligible.
What I'm talking is about what is the constraints which are needed in order for a binary black hole of primordial origin to be formed. And there, which is the metric in which you study the behavior of this black hole is important. So if you take in the source...
I understand that what you are saying because
I mean, I cannot explain it.
I mean, you are just assuming that it is important, but I can tell you
It is important. It is important at these early stages that they were formed.
So no, it's not because this is, I mean,
Maybe you can discuss later.
I mean, look at the simulations and then that's what you see.
Your simulations, I don't know what you did, but I said if you take this kind of assumption, this is not correct. What are your simulations? I don't know.
A man of the
Correct
most...
statement that goes back to
Anyway.
things that we know.
Maybe you can discuss later. One more question?
You mentioned the thing to do will be to test qualitative predictions from quantum gravity. Now, there seems to be an emerging agreement within some part of the STEAM community that there might be one or two extra dimension of the micron size. So do you think that this would be tested with future gravitational wave?
There have been constraints about that. I had a slide from the PNS, the one with the GRP, Digital 1770, from exactly as I put it there, if you find from the interferometer what is going to be the gravitational wave luminosity, and then you have from your electromagnetic counter when it's going to be the EM luminosity, then this depends on the dimensionality of space-time, because you might have some kind of gravitational waves that leaked in the extra dimensions, and then the collaboration really had put some constraints on that. And there is a model, there's a couple of models that have been constrained from one event. That's all I can say. Okay?
You need to do what? Sorry.
This question that you have, I mean, the size of extra dimension, if it's, I mean, current bound is like around 30 microns, so So if we have extra dimension of that size, how can it be constrained by gravitational waves? I mean, say gravitational waves are much longer.
The constraint which was put was the number of the extra dimensions. I can show you the formula of the number of extra dimensions.
But that must assume some other underlying model.
There are two free parameters, the number of extra dimensions and the RC, which is the distance beyond which you can leak in the extra dimensions. And there was some correction. Actually, there was a constraint, I think it was your model.
Yeah, that's why
I know. That's why I removed the name of the model that has been constrained. I knew you were going to scream. So now that you put it there is a constraint from the collaboration. I don't know the extra assumptions that were put together. I can show you the formula and you can tell me
the
something.
was out, but if it's still hopeful, very good. So I thought my model was out.
Yeah.
But maybe it's not.
There is a constraint that is put there. I can show you.
Okay, good news. No.
I cannot. It's also true. Yeah, it's also true that I don't know, to tell you the truth, if there are extra assumptions that was made there.
No, I'll be very happy.
Yeah, I can show you what it is and we can discuss. I don't know the extra assumptions.
Okay, thanks.
But the assumption, the constraint goes on the number of the extra dimensions, not on the.
No, I understand. Thank you.
More questions?
Yes, I have a question for Francesco. I had expected that you first consider the prototypes of black holes, the simplest possible black hole, the instruction one, where you have cosmic censorship, at least for the future event horizon, for the future singularity, you have cosmic censorship. And so it seems no way that it can do it now. The past singularity only comes about if you integrate if you assume black holes have infinite life. If you think that he formed cosmic event, then there is no, strictly speaking, there's no past singularity at all. So, but you seem to be starting to jump in deep. What you have to send, you go to the deepest part of the point and you jump. That doesn't seem a very good strategy to my mind.
So I mentioned at the beginning the cosmic censorship projection, and it's a very practical way to deal with the singularities and this problem. I just the first slide I was mentioning. Okay, let's imagine jumping to the black hole, right? So it's true that we can, for outside observers, make sense the theory remains predictable and everything is fine if you assume the weak and the strong censorship projection. But in my mind, it's still unsatisfactory that we have a region of space-time that we can access. We can jump inside the black hole. We cannot go back. We can jump inside, and the theory will stop working there. I don't know if this was your point. I mean, I agree that it's large in black hole, and for outside observer, it's perfectly fine. This is totally completely agree. But we must still ask what happens when you go inside. You know? If I jump inside the black hole, something will happen to me, and the theory is not able to tell me what is going to happen. And this is my opinion on bit unsatisfactory, but
it seems to be very difficult to get the signal from a singularity.
Yeah, absolutely. This is, this is what I was saying at the beginning. Like, this is definitely a place where the theory stops working, but it's also a place where it's the most difficult, if not impossible, to get a signal. So, but the point I was trying to make is maybe studying it and trying to understand. Maybe we get some qualitatively new feature that can arise. And when I started working on this, I was much more pessimistic because I thought, okay, you just make a small modification in the interior, but then it turns out it's not so easy. I mean, there are a lot of problems. If you want to constrain your modification only in the interior, you arise a lot of problems, of course. I'm not claiming it is not possible, and even it is not unlikely, but there are problems also there. So there is worth in studying with an open mind, and if you are lucky, you will find some new feature. If you are not, okay, it's life.
Questions? No, maybe I have one for Masaide. So
which are the models that are amenable in your treatment, and what happens when you consider this quartic contracting patterns? So you had a slide that you didn't show.
Okay, you mean the higher order correction of the Taylor potential. So in that case, you see, Hubble correction is never universal. So even if we can get information of the difference of the mu or mass, it's never cancelled. So you see, bare mass plus 2 Hubble square minus bare mass plus 3 Hubble squares, they're always Hubble dominant. So we cannot prove the bare mass. This is the problem. Only when the, you see, Hubble correction is universal, it's cancelled, then we can prove the bare mass or, you see, current mass. This is the problem, and of course, you see, in our example, it's completely ideal. So once we have such a higher order correction, or as Gia said, you see, if we integration is realized by the data, we don't have such a Hubble correction. So maybe, yeah, we need to go beyond some new idea. Yeah.
Thanks. Also a question for Francesco. Which kind of models give rise to this non-singular black box? You consider higher derivative or local?
Yeah, so as I said, I was trying to focus on things that are kind of universal. There are a lot of models, a lot of toy models.
To just study stability, you need dynamics.
So there are, like, to study most of the aspects of the stability, yes, but I'm just studying the perturbation on topology space-time and show that at the linear level you have this huge back reaction. Now, to study whether or not this back reaction, what is the endpoint due to the back reaction, then I will need dynamics, and there are a few works in I was mentioning one in just semi-classical gravity and resonant non-ground, which stimulates pretty even though it's a black hole. There is something else. I mean, there are a lot of models to give you this type of options. Models inspired by quantum gravity, because it is safe, for instance, some or models in higher derivative gravities. For what I mentioned very quickly, that there are few possible classes of non-singular spacetimes, implies that a lot of different models give you something which looks very similar to each other, and so that's why I thought it's nice to see if you can do something that kind of applies to everything, even though it's not valid, because there are assumptions. Yeah.
Thank you. Is there any more question? Otherwise, we move to the discussion. So we can. So well, I will pose an open question, so you can give me your view about what is, up to you, the most challenging problem in physics, where we can gain more insight, more generic. So of course you all have, we come from different areas, different things. For instance, it's the Hubble potential. What's your opinion?
Well, to me it's not Hubble potential, because I think this is something that is going to be resolved hopefully soon, and I don't think that it's fundamental physics. I don't think it's fundamental physics there. I think the most important thing is to find a robust way to describe the data we have from the universe without using ad hoc models. So it seems to be that we need an early late accelerated expansion, and I would be interested to see the kind of quantum gravity effect, because I think these are purely quantum gravity kind of effects. Dark energy and what is the dark place. Both these things should be quantum gravity. Not dark matter that we have candidates, I don't think it's the case. But for early late accelerated expansion, I think it's a quantum gravity effect. And it would be good if we could find some more about it. I mean, that's, I think, a way that both theory and experiments have to work hand by hand to find a solution. Keeping an open mind.
So, yeah, my guess, biggest problem or biggest question why I came to this field is to know what's the real concept of the universe, what happens before inflation. And typically, if such a scale, even if it exits the horizon, it's still currently in the super horizon. So people claim that we have no way to grow it. So we don't have any method to grow the epoch before inflation was the real concept. But I would like to violate or break such a common sense and go into the details such a this is my dream.
But it's very difficult to answer because the fundamental problem we have a few I talk about singularities, of course, finding interesting, there's quantum gravity. But then the second part of your question was when we're going to make progress. I don't know. I think at the moment, I was talking about black holes. If you want to really find trace unique physics of black holes, at the moment there is so much we need to do, even before thinking about the physics, about about astrophysics, like we've seen the years about waveforms, not a waveform generativity. So unless we have something which is huge or qualitatively new, as Mary was saying, we are not going to see it. So we need to do a lot of modeling in order to see it. But I'm a bit pessimistic that this is going to happen because of how academia works. Because if I start and take my career developing waveform in a random theory of gravity, I will not find anything after my PhD. And this is I don't know. And on the other hand, we don't have a really extremely good candidate who justify putting all the work you're putting in generativity. So I really hope that we will find something qualitatively new. You mentioned the equals. I don't think they will not be there because that's too simplified. So either we find billion, we're so lucky it's going to be something huge, or it's going to be qualitatively new, we have not found yet. Or for a very long time we will see. I know this is pessimistic, but this is how it's for relation. Then I don't know, in cosmology, collision waves from the coast. Maybe in cosmology would be luckier. I don't know. I hope so. But I hope that Luca will organize the same conference in 5 years and I will say, okay, I was wrong.
I was hoping for next year.
Next year, I think Luca took 2 years to organize this conference, so I don't know if it will be 2 years.
Maybe enough for more progress.
So the question, what is the most important problem in modern physics? We say the most important problem are the phones. First of all, money. That's the basic problem. The money. That's the first big problem, I would say. Apart from this, just a consideration, because as you said, we come from different backgrounds. My background maybe is a bit different from the others. I think it's very nice to, quantum gravity is very important, to understand. It's very challenging, but there are still so many things to understand that, let me say, at much lower energy, like, for example, I showed we don't know how to describe neutrinos in quantum field theory. We don't know what is correct interplay sometimes between subjects from quantum foundations or in quantum informations and relativistic quantum field theory. I don't mean general, I mean special relativistic quantum field theory. Is some of you capable of describing entanglement in weak interactions, for example? It's there are Orsilin electrodynamics. There are so many things that should be understood that I don't know. It's very difficult to answer, but I have the impression that sometimes we are looking at the moon, that is very good, we dream, but we still have so many problems on the Earth that we will reach the moon one day or another, but I don't know. Okay, so that's my general consideration. I don't have a precise answer in this sense.
Yeah, something small. I didn't want to sound too pessimistic because there are things that might be like depend very quickly on astrophysics. For instance, if you look at the images of the course, and if you're able to increase the precision so that you can see the light rings. The position will depend very deeply on physics. It may be something that if it's the violation that we expect in VR, we might see maybe universal, maybe new gravity, and then this will boost a lot the studies of new theories. Again, gravitational waves maybe we will see some violation on modular theorem, and this will boost a lot the study of alternatives. I mean, it could be that it will be, but of course, it's not so likely.
And the problem is, given the catch in funds in the years to come now, particularly we know that the catch in funds for LICO, then the US is out, and all that, so many of the things might be postponed a bit even more than what people thought before. There's less funds.
Okay. Any comment from the audience?
Maybe I can ask you. Although you say that likely equals are not there, but couldn't it be that they are just 90 and at the moment they cannot be resolved?
Up to now, at 90% confidence level, it was not enough.
Okay,
Whatever
but this
that
doesn't
means.
mean anything.
It means up to now, they cannot be 90%.
I think there is a bigger problem than the fact that we have not seen the medics. The way we found that we introduce eco, it's a very nice idea, it's beautiful, but it's just we take perturbation on top of a fixed background, which is boundary condition different from GR, but it's a Schwarzschild vector. And if you study the perturbation on top of Schwarzschild vector, then we see this periodic signal. We might be able to find it because it's periodic and it looks exactly like the wave from GR, and it's amazing. But as soon as you go beyond this, even ignoring the fact that maybe we don't want to use Schwarzschild and so Reggie-Williams ability to study the perturbation, as soon as you go beyond the perfectly fixed background, even a tiny modification of the background due to this will give you a huge difference. You will not see a periodic structure, you will not see the perfect repetition, and also in a lot of models the time between ecos is huge, even if they exist in a huge time scale. So we really don't know at the theoretical level what to look for, because what we're looking for is so idealized that it will never be there.
The problem is that all these kind of exotic things, they are very much model dependent.
Yeah.
So there is no generic way to look for it, you see. And therefore, it's what I said at the end, go to these exotic models to find that you have a black hole. And that this is a stage of one, to go to other. And this order is for this exotic model that may look lower. It's a lot of work that people don't do. Because at least be motivated, at least to pass some tests, otherwise it's a PhD thesis of 10 people for at the end of the day to say, oh, that was completely. So it's not simple. So that's why I was keep saying some qualitative effect that you can see, and then so it has to be step by step, otherwise.
Well, probably not all the qualitative effects can be distinguished, at least not in the radiation waves, maybe.
It's no model dependent. To go to calculate the wave from this particular node.
Yeah, qualitative value also. Have an idea of the qualitative effects.
That's yet another, that's yet another level where much more model dependent we can solve. I mean, people rush to that before doing the distribution. I think we test a particular human model.
Some comment from the audience?
Yeah, I'd like to kind of go back to what Mary's point about the fact that, like in the case of inflation, etc., the data does not confirm a theory, but just shows consistency, basically. So that would essentially also tell us that it's very important to pay attention to the development of consistent theories, because even if you look historically, when general relativity was formulated, there was no experimental evidence for it. essentially arose from the issue of consistency of the question of consistency of special relativity with gravitation on inertial frames, etc. And similarly for the Dirac equation, there was no, it arose just from Dirac's kind of curiosity of investigating the inconsistency of first quantized theory, basically. Similarly for Yang-Mills theory, so in all of these developments, of course, observation and data is extremely important, but in none of these cases, the theory, okay, in none of these cases I mentioned, of course, in other cases that's not true. The development has not come precisely from data, even in a standard model. If we try to construct a standard model from the data that we had in 1970, for example, it would not have been possible. It was the requirements of the unitarity, normalizability, etc., that led to the development of the theory, which of course predicted things way beyond the available data. So I think at present also, and this was actually brought up by the comments that you made, that it's also important to consider the development of consistent theories in parallel with improving observations and experiments, for example. And that generically, if of course one has to go by experimental data, and if that is not available, then of course the way that people have used for decades or maybe centuries is to look for inconsistencies within existing frameworks, which people do in the context of information, black hole information, quantum theory, black holes, etc. And from there, like, push that and try to develop consistent theoretical frameworks that then can be tested by observations.
I agree.
Yeah.
I agree. Thank you.
Okay. Any final comment or remark?
So if not, we can end this session. I would like to thank all the speakers of this morning.
So yeah, we will start again at 3 o'clock the round table. Regarding the buses for tomorrow.